So we're trying to do ensemble methods today, bagging and boosting. We went over bagging last time. We're going to do that and go on to boosting. Couple of administrative notes. So homework 3 was due yesterday, 4 will go out soon. We did this. I know a few people are still taking videos and participating, trying to upload things to channel. So we'll do that on Monday. You'll get hopefully your prize and hopefully. Well, we don't know if you were over.
But there are people who have come really close.
Yeah, but we don't know if all of you are overfilled. I don't know. We'll see that.
Yes.
Okay. Just a, yes.
When will the next homework be due?
We'll probably go out. What?
Before 29.
Probably not. So the next homework will probably be smaller than everything that you've had so far. We don't have a lot of time left. We also need your project final, the finishing thing to happen. So it'll probably be much shorter than everything else. And it'll happen sometimes towards the end. It'll be due end of April or we might actually. I've actually had one of my students build up a really nice implementation. It's an IM to text application, so you're given an image and you're training a neural network to generate a sentence. But it may be too much to actually put in the last one. So it was a really nice thing that we've built up, but we may have to just wait. We'll see how long. I'll look at the time. We'll have to wait. Okay, just a quick reminder, Monday we're doing the remaining presentations. Alright, so let's go back. We're talking about ensemble methods. And our motivation was a figure like this, where we said that if there are two classes of, at the end of the spectrum, there are weak learners and strong learners. Weak learners will generally have, this was a regression problem, they will generally have high bias but low variance. So if you had another data set like this, the straight line that you end up learning will be slightly different but not too terribly different. On the other hand, a 16th order polynomial will grossly overfit, so will give you really low bias but high variance between two different data sets. Right? And we said, okay, so at the ends of spectrums, simple classifiers like naive Bayes logic regression, decision stumps, so extremely shallow decision trees, are good in one end, they have low variance. And sophisticated learners are good in the other thing that they have low bias. Can we combine these properties? Right? And we are going to discuss two ways of combining these properties. The way we're going to do this is by learning a committee of classifiers, right? Not a single classifier. And the output will actually be a weighted combination. But the way we're going to do this, or actually just, weighted combination. But the way we're going to do this is bagging and boosting. Bagging is going to work with strong learners or sophisticated learners, and the idea is going to be that on average they will do better than a single classifier. You're trying to reduce the variance of strong learners. And boosting, the idea is that you're going to take a weak learner, so on your training data they will make, each individual classifier will make lots of errors, but by combining them, each one may be good at a different part of the input space. This is just an intuition. And by combining a bunch of them, you will try to boost up, you'll try to increase their accuracy, right? So you'll reduce the bias of them. Does that make sense? So we looked at the first one last time, the idea of bagging, and I thought I'll show this demo of Bootstrap Sampling, which I really liked. So this was a really nice demo. And the idea was that there is some underlying distribution. You don't get to see this distribution, right? Think of this as P of X or P of Y, right? You don't get to see that distribution. You just see a sample from that distribution at any given point of time, right? So these are the samples, right? The ones that you see are samples from that distribution. And in statistics, they're interested in quantities that they want to estimate about that population from this sample, right? Let's say mean. We're not interested in simple quantities like mean. What we're going to do is train a classifier on this to predict something, right? But the intuitions are going to be the same, that you actually see a sample. Let's say you actually were to compute the mean from this sample. You know what the mean of this sample is, right? But then you have no sense of variance. You don't know how much is this mean going to vary if I get another sample, another data set from this distribution. And so the idea of bootstrap sampling is that you take your sample that you have and you resample from that So create a new data set which also has the same number of points as this, but you've sampled this with repetition, right? So like this point I think got sampled 3 times and so on, right? So I think in the original distribution this was sampled twice, here it got 3 times and so on. The total number of points is the same, and then you use this resampled data set to compute, let's say, the mean, right? And then you don't just do this once, you keep doing this, right? You just keep generating new samples from this thing, and at the bottom it's computing a histogram of all the means that you're computing. Right? So every time you draw a new data set, you compute a mean on that new data set, right? And you keep a track of all those means. And if you do this a long time, you end up with a nice little distribution from which you can draw confidence intervals. Right? So now you can say, here's the 95% confidence interval from how many times have I resampled this. And there's some really nice theory which relates these confidence intervals to the ones that you would have got from the underlying distribution. Right? That makes sense? That idea makes sense? Yes?
So is the idea that by resampling you don't change the variance of the distribution?
In a way, yeah. By resampling, what you're doing is you're creating new data sets and you're computing estimates from each one of those data sets. And whatever you're trying to estimate, in this case mean, the sense of variance that you get from each one of those 2 data sets does tell you something about the sense of variance that you would have gotten from the underlying distribution. And under certain conditions you can relate the two. We're actually not going to be too terribly interested in those sort of conditions, right? Because we're not interested in simple quantities like means or so. For us, every time we get a data set, we're going to train a heavy machinery, for example, decision trees, neural networks, whatever. And so what we are estimating is not this mean, what we're estimating is a mapping from X to Y, right? And there's going to be heavy variance in that mapping that you end up learning. And by averaging across all those data sets that you have generated, you get a better sense of what you would have gotten from that tree distribution. Does that make sense? Yes?
So like every time the original sample data didn't change, it was just you were resampling?
Yes, that's right. So in practice, you should think of this as the data set is really expensive, or it takes a lot of, like, you have to conduct human studies, right? Or annotating this data set took a lot of time. And so this is what you have, right? And you cannot get any new data sample from that original distribution, but you can get resamples from that distribution.
But the first distribution is samples, and the second distribution is resampling means. So why do we change it? So what's the difference between
No. So here I'm just keeping track of the distribution of the means because ultimately I want to give you confidence intervals on the mean. But if I wanted to keep track, if I wanted to predict some other estimator, like if I wanted to predict, the mapping from X to Y, then I would keep track of all those mappings and I'd give you some sense of variance on those. Right? So this is your estimator that you'd like to estimate, whatever it may be. Right? Yes.
So hello, didn't we end up with this resampling distribution, no matter what the distribution of the?
Yeah, that's the cool part. So no matter what that is,
we'll end up always with this.
No. So you don't always. So you can change the underlying true distribution, and sampling from that underlying true distribution may be hard or it may be expensive. But this sampling is always easy, and the observation that you're making is that this distribution always tends to look like a Gaussian. It's because you're always computing that estimator, right? And it's like central limit theorem kicking
Because
in.
the mean will be always near the center of this
Exactly.
data set.
Yes.
So there are some cases where you have a model trained on some data, and then you have some new data that's streaming in, and you want to adapt your model to that data. Would this be a fit for such kind of application?
Not off the top of my head, because here you're not off the top of my head. Usually, when you have that streaming online setting, online learning, and which is what we haven't seen in class, usually applies when you have a single model and you want to update the parameters of this model. So you want to very quickly warm start. I had a data set of 10,000 points, now I have 10,200 points. Can you quickly update my parameters that I had trained on those 10,000 points? And then you have these online methods. Or you have a dynamic system where data distribution might be changing and I just keep seeing samples, and so I'd like to always be adapting to the samples that I'm seeing. here, because there is one separate data set every time, and that data set has been resampled from a fixed size, you would have to keep track of all those. Like each one of those would have to increase as well, right? So if this was a data set of 100 points, and you saw 20 more points, each one of these new data sets would also have to resample from those 20.
Oh, okay. So I was thinking that the new data that you get, you could consider that as a new sampling. Would that make sense? Probably.
Except it's not sampling with replacement from that original thing, right? So, like, because I'm not getting into the details of how you can relate guarantees here to guarantees there, and that's where. Any other questions? Okay. So stepping back, so this was just the idea of bootstrap sampling. For us, bootstrap sampling is sitting in an inner loop of learning, right? So every single data set, you learn a different classifier, you end up with a committee of classifiers, and then you average the things. Either you're averaging probabilities, or if you're doing regression, you're just directly averaging the outputs. And last time we did that derivation where we showed that if you make two assumptions, one is that you're sort of making zero mean errors, and the other is you're making uncorrelated errors. So different data sets that you have are making uncorrelated errors, then the committee's average error, the committee's error is going to be 1 over m of the average errors, right? And that relied very crucially on that uncorrelated assumption. Right? It was this idea that when one person makes a mistake, you cannot predict that the other person is also going to make a mistake in a committee. That makes sense? That's why averaging helps in that case. Anybody here co-advised by 2 faculty members? We have 2 advisors. Anybody here recently deciding on a thesis committee or a project? You know what uncorrelated committee members feel like. You walk into a room, one person says one thing, the other person says completely something else. They're being completely uncorrelated with each other. They're hoping that you will average their views out. And as a committee, you get more sort of thing out of it. Right? Theory says that's the right thing to do. We're doing it because it's optimal. Okay, and this idea is used in practice with strong learners like decision trees. Each decision tree will overfit, and we know that bootstrap sampling is not going to get you decorrelation, right? The things are, because the same data points are appearing in every single resample, these things are not going to be truly uncorrelated, and therefore you try different things like train this on some subsets of features, train this on some other subsets of features, train this on some other subsets of features. So people try different heuristics to make ensemble methods as decorrelated as possible, because that will generally help after averaging. Does that make sense? Okay. Any other questions on this? Okay, so this is the high-level idea of bagging, and now we'll move to different kinds of methods, which is boosting. The idea in boosting is going to be you have an extremely weak learner. So this is a strong learner. Each one can express a sophisticated decision boundary or concept. We're going to work with weak learners. Each one by itself on a 2-class problem may be barely doing better than chance. And that's going to be crucial. We're going to ask weak learners that at least beat chance by some non-trivial margin. So in a 2-class classification, if the classes are evenly balanced, we're going to ask that the weak learners do better, strictly greater than 50% in terms of accuracy. And what we're going to do is by doing weighted average of weak learners, we're going to put together a strong learner. Does that make sense? So let's write down the board. Boosting ideas, reducing bias in weak learners. Okay, so the first thing we'll talk about is a space of weak learners. Right, so we've been talking about hypothesis classes all semester. We're going to try to get more formal with that. So there is a set, each item in this set is going to be a weak learner. And I'll give you an example. So example number 1, for binary classification, a weak learner may be a decision stump. So this is a decision stump. It looks at a feature xj, checks against a threshold, greater than or equal to t, less than t, and it just says if you're greater than t, then h of x is equal to +1, less than h of x is equal to -1. This is what it does. This is an extremely simple learner. If you think of it visually, this is what it looks like. There is some feature xj, there is a threshold t on, and this is the decision boundary. Right? On the right side is plus, on the left side is minus. This is an extremely simple learner, and if I had to write this down in a set theoretic notation, I would say the set of j, comma t, these pairs, where j can be 1 through d, and t is a real number. This is the space of all possible weak learners. Pick a feature, pick a threshold, and you have a weak learner. That's why it's this tuple j comma t, the set of all possible such tuples. That's this set. Does that make sense? So this is our space of weak learners. Each item in this is going to be a weak learner, and we're going to pick a collection of weak learners, combine them to create a strong learners. Yes?
What does J represent?
J is the index of the feature. So xj greater than threshold, xj less than threshold. Yes?
So every weak learner is going to learn only based on only one feature?
In this example, yes. There are going to be, I mean, you can always choose other weak learners as well. I'm just choosing something simple, and you'll see that this is just an example. I won't actually do anything specific with this kind of weak learner. I'll assume that you know how to train a weak learner, and we get to that in a second. Okay, here's another, so this was for classification. Here's another example, which is decision stump for regression, right? Decision stump for regression. Here's what that does. It does again the same thing. Takes a feature xj, checks against a threshold. But at this point, after you've divided your data set into two buckets, you actually have to make a prediction. And here's one way of making a prediction. So you can say h of x or y is 1 over, so I'm going to denote with left and right as data points that have this, that fall in this bucket, right? So what's the R is set of data points with xj greater than. Right, so all training data points that fall on that side is R, all training data points that fall on this side is L, and here's one way of making predictions. So this is a decision stump. What it does is it picks one feature, checks that feature against the threshold. If you're on the right side of the threshold, it averages all training data points that had previously in training, all training data points that also have that feature greater than threshold, and just gives you the average value. Visually, it looks like this. This is xj, this is that threshold, and this is what it does. Right? This is the average on the right side, this is the average on the left side, so you end up just learning piecewise constant functions, where there are only two pieces. Right? And it's pretty clear that I can also generalize this, right? I can make this piecewise linear, for example. I can do one linear side on this, one linear side on this. I can have one weight on this, one weight on this side. Does that make sense? So that would be another sort of weak. So I would have to choose a feature, choose a threshold, I would have to choose a weight on the left-hand side, a weight on the right-hand side, and this tuple, the set of all possible 4 tuples, that would be my weak learner class. Does that make sense? Pick a feature, pick a threshold, pick a linear combination on the left, pick a linear combination on the right, and that's a weak loop. Does that make sense? Okay. So these are two examples of weak learners, one for classification, one for regression. And what we are going to do is we're going to assume that given a data set, you already know how to, so this is what we've been doing all class, that learning is optimization in this set, right? All that learning means is you search your set for a weak learner or a strong learner or whatever that minimizes some loss function. We're going to assume you know how to do that. Right? That's a black box. That's what we've been doing entire semester. Whether it's linear regression, polynomial regression, decision trees, whatever. There is some algorithm that you know that can do one thing, and I'll write that down. So black box. That min, so you're given a data set, given these are x1, y1, so xn, yn. Given some data set, you know how to do this. Minimize the normalized loss of yi, comma h of x. H belongs to weak learner set. There is a data set of n data points, input, output. There is a loss function. There's the average loss over the training data. And you can add a regularization in there. I don't really care. I'm just making this simple. And this is all of machine learning in subsets, right? All of supervised learning. Define a hypothesis class, whether that's SVM, decision trees, whatever. Minimize this over the space of learners, and we're going to assume you know how to do this. Okay? And what we're going to do is we're going to make repeated calls to this black box to learn a collection of weak learners. Does that make sense? We're going to assume this is possible, and this is going to be a function that we can always call in an algorithm. So boosting will make repeated calls to this. Does that make sense? So the goal of boosting is to learn a linear combination of a bunch of weak learners. So it wants to learn summation of alpha t ht of x, where there is some enumeration of t. Right? So pick a weak learner ht, add it to pick a bunch of weak learners, add them with these weights alpha t. Right? And the goal of boosting is minimize over alpha t and ht 1 over n summation I equals 1 to n of loss yi, comma f of x. Does this make sense? The difference between that and this is for a single weak learner. You know how to find one weak learner h in this class. So it's a single decision stump that minimizes the training error. And this is a collection of weak learners, f, where f is a linear combination of weak learners. And you're optimizing for both which weak learner to pick and how to combine them. Which weak learner might be a decision stump, each with its own feature and threshold, and how to combine them is just some number. Does that make sense? So it's alpha t in R, h t. Okay, and the thing that boosting does is it says, all right, that's too hard. That's a joint optimization problem. There's a bunch of alphas, there's a bunch of h's. We're not going to do that. What we're going to do is we're going to realize that this summation, it's alpha 1 h1 plus alpha 2 of h2 plus alpha t, so alpha t minus 1 h2 minus 1 plus alpha t h2. We're going to say that this summation, boosting is going to be a greedy algorithm. It's going to proceed in rounds. What it's going to say is that at time t, I'm going to assume I have already learned this. I have already learned how to combine t minus 1 weak learners. I've picked t minus 1 weak learners. I've combined them in a good way. And at time t, I'm just going to optimize how to add one more weak learner and the weight with which I should add it to the ensemble. Does that make sense? Yes.
Is this thing related to threshold?
No, it's not. I really want that T. This is the threshold, that's time.
That's fine, that's fine.
That's fine, that's fine, that's fine.
Okay. Context switch. Just forget about this T. I'm never going to talk about this T again. Okay. So this T refers to iterations or time. Boosting proceeds in rounds of boosting or iterations of boosting. So at time t, you have t minus 1 weak learners and their combinations learned, and you'd like to learn that. And the way boosting is going to proceed is that, so this problem is too hard, right? And we're going to convert this into min of, so this was over all alpha t's, all h t's. We're going to just optimize alpha t and h t of this thing, assuming this is all fixed. And I will write this down in a second. I'll first show you a demo. And what boosting is going to do is this optimization problem of picking a scalar and a weak learner, it will convert this into a black box call with an appropriately defined y. Right? Does that make sense? And it feels like it should already be possible. Right? If these things are fixed, then f just consists of a constant plus. Right? This is just a constant plus alpha times weak learner. We already know how to optimize, this thing which is just different by a constant plus a bias. So we're going to convert that problem into an instance of this problem. Does that make sense? And we're going to do that differently based on what this loss function is. If this loss function is squared loss for a regression problem, it's going to be called LT boosting. If this loss function is classification loss, so we're going to define something called an exponential loss, it's going to be eta boost. Different loss functions are going to lead to different boosting algorithms. But they all essentially have this same flavor. Collection of classifiers, proceed in greedy optimization, and reduce to a black box order. Does that make sense?
Can you prove this approximation algorithm to the real optimization value?
Yeah, so it's a greedy algorithm, and you can actually, we're going to make an even stronger claim, and that claim is going to be for classification that as t goes to infinity, if you allow me infinitely many weak learners, that training error of this weak learner is going to go to 0. So if there exists a collection of weak learners, if I can always find a weak learner in this hypothesis class, each of which are better than random. Right? So if you can give me a weak learner that's just slightly better than chance, 2-class classification, it does 50.00001. Right? That's the accuracy. If there's a bunch of those, I can combine them, and I can, on training data, get training error to go down to 0. So I can cover the spectrum from completely weak to completely strong just by adding enough weak learners. Does that make sense? So that's what the theory says. So let me show you a demo next, and I'll come back to this derivation. And one slight change for the demo to prepare is just going to be the ability to handle this as well. Right? That it's not just loss function, it's a weighted loss function. That every data point is allowed to have some weight, something like I value this data point 10 times more than that other data point. Right? And typically most of these training algorithms accommodate that as well. Okay, so let me show you a demo for boosting, and then we'll come back and derive this.
The data is the same here at every call, right?
Yeah, the data is the same. You only have one set of training data. You just learn multiple classifiers. Each one of them will actually be trained with a different weighting. And we'll tell you exactly what.
Yeah, because without weighting, we will have always the same
Yeah.
H
Yeah.
weak learner.
So either we can change the weighting or we can change the label, and we'll do both the theory and the. I'll show you that. Okay. So weak learners, you have a black box that can train this weak learner at each iteration. You update. Okay, let's see if we can go get that. Alright, so here's a demo. I'm going to construct a data set, and I'm going to, the weak learner here is going to be decision stump. This is going to be a classification problem. It's a 2-class classification problem. Let's see. Here's my, green is too light, isn't it?
That's good.
Right. So this is one class, and this is another class.
You like this one?
Oh, error. No worries. So this is, remember our weak learner is a decision stump. So you can pick, there are only 2 features. It can pick one feature and choose a threshold. It can pick another feature, choose a threshold. That's all it has. Yet it's somehow expected to carve out a decision boundary for this, with maybe even this, who knows, right? And so this is what, so this is iteration 1 of boosting, right? On the left, it learns a single weak learner. The weak learner picks this feature and chooses this threshold. So the positive is, I think, class 1, negative is class much, right? So it got all the green points correct. It got these red points wrong and these red points correct, right? So now these red points which were wrong in the next iteration will have their weights increased. So now the second weak learner has again the same data set, again the same class, but has to focus more on these points. Does that make sense? And this is the second weak learner that it picks, right? With the second weak learner, the circles have increased in size because these were more important. And it picks, again, this feature and a threshold, and it says, okay, that one is positive, this one is negative, right? And so it gets these ones correct, makes a mistake here. The mistakes will have their weights bumped up. And on the right is a cumulative sum. So it's alpha times h1 plus alpha 2 times h2, right? And so far, this is the decision boundary it has carved out. Right? So we're getting there. This is round 3 of boosting, and these points had become even bigger, and therefore these points had become bigger, so it decided to focus on these points. Let me get these points all correct. These ones are incorrect, so these points will get even bigger. And so this is round 4, and so on. So it's at this point it has sort of carved out this nice little decision boundary. It's getting all of those points, and I think it will still try to get that one data point, right? Because all of these weak learners, at this point it's done. All of these weak learners can make a mistake on that. At this point it has carved out this decision boundary, 100% training accuracy, and then it stops. There's nothing to do. Right? Every data point is being correctly classified. So if I plot on the x-axis iterations of boosting, and on y-axis error, there's a nice decaying trend. You took an extremely weak classifier to an extremely strong classifier, and you covered an entire spectrum from weak to strong. Does that make sense? Make sense? Yes.
What does one iteration here means? Does it mean one weak
Yes.
learner?
It means one weak learner.
And you had 2 features?
Yeah, there are only 2 features, x1 and x2, two-dimensional.
But you had 4, like a total of like more than 4 weak learners, right?
Yeah.
So
Because the weak learners are pick a feature, pick a threshold.
yes.
The hypothesis class is infinitely large.
Oh, okay. That's
Right? You can pick any feature and you can pick any threshold. The features are discrete, they're finite, but the thresholds are infinitely large.
Okay. I was gonna ask how many weak learners do you choose, but you told me it's infinitely large.
It's infinite. The real number is set as infinitely large.
Yeah, every iteration, how does it automatically pick which feature,
Yeah,
randomly
so
work?
that's what we'll do in the board now. Now what we'll do is, how is it that this optimization of alpha times h was converted into a black box? Right, so there's a black box that you know how to pick a decision stump. How do you pick a decision stump? We already looked at that in decision tree lecture. Right? It's a single depth decision tree that you know how to train, and we're going to make multiple calls to that function, and we'll do that in one go. Yes?
So how do you decide how many simple classifiers you use? It's like until you achieve 100% accuracy on training data?
Exactly. So you can. This is the spectrum between a weak to a strong learner, right? So this is the same question as model selection. How do I know whether to choose linear classifiers or neural networks or the depth? And on the x-axis is model complexity. As you keep doing iterations of boosting, you're creating a stronger and stronger classifier. So what you have to do is you have to hold off some validation data. So the training accuracy error will always go down, validation will go down and up, and that's when you know you have to stop. That makes sense? Yes?
Like, I guess, like, how well does this work? Because it seems like really nice to use such a simple, like, could you achieve something like performance like a complicated neural network or something with really simple?
So you have to, every class I've taught, right after this, there's a variation of this question, which comes, can I combine bagged decision forest and can I boost bagged decision forest, right? This, you have to think about this, right? The strength of this is that you have a weak learner and you have a collection of weak learners, and they have low variance and high bias. And you're putting together a bunch of those to create a strong learner. But if you put enough of them, it will have high variance again. Right? You have created a high variance classifier. And so you don't want to already start with a high variance classifier like a deep decision tree or a deep neural network. Right? You don't want to do that because it's already overfitting. And what you need is the exact opposite. You need to average a bunch of them out so that they stop, so that their variance is reduced. That makes sense? Any other questions? Okay, so let's take a minute and then I'll do the derivation on the board. I just want to make sure we don't have
So we're talking about boosting
so each strong, we're calling them strong, but we should call them overfitting. So you're taking each overfitted learner and you're making them by application. We will not increase the bias, we actually decrease the bias. There's a whole bunch of things. So think of the spectrum. Underfitting, strong weakness, a huge standard. This one, underfitness, you're making a small. Yeah, if you line too much, then you have extremely large number. You may actually have less than optimal combination.
Yeah, my friends that were like Oh, man, it's like a day. We're going to be bowling in the morning, we're going to be bowling in the morning. Yeah, we're doing groups of surprise things. I am probably so probably very Sunday, which is 40 days, we have a big choir concert on Sunday. So I'm gonna be like, it'll be okay. But yeah, so it's gonna be interesting because like we're going out Saturday night and then I have to be here on Sunday morning and we'll be there. But I know you leave,
So, like I mentioned, boosting can be used for regression with squared loss. So y minus f of x squared, that would be the loss function. We call that sort of an L2 boosting algorithm. You can use regression with absolute loss, in which case you call that a gradient boosting algorithm. Classification with something called an exponential loss, and you've met this in your midterm. With that particular loss function, that's called an ADA boost algorithm. And log loss or logistic loss is called a logic boost, right? And that's kind of why there's sort of so many families, there's so many instances of boosting algorithms, right? What we're going to do today is we're going to look at this sort of a derivation. We're going to assume regression, L2 loss function, and we'll tell you exactly how to write down this boosting algorithm. Right? So let's do that. We are here. We have at iteration t up to t minus 1. Weak learners have been trained. Their linear combinations have been trained. Our goal is to pick alpha t and ht so that it minimizes this. And now, right? And I'm going to say not just all. So the only minimization is over. The only minimization is over alpha t and ht. Right? So all of these are fixed. And this is squared loss, so I can say yi minus f of xi squared. Right? That's the loss. This is the minimization that you'd like to do. And remember, the black box solver that we have is also yi minus hi squared. Right? We have access to this. We know how to solve this. This is called a least squares problem, right? So here's what we'll do. Let's just plug in what this stands for, f of x. Actually, I'm going to use a little notation. I'm going to say
Constant.
I'm sorry?
What does say constant? Oh.
Yeah, constant, exactly. So all the way up to this, I'm going to say this is f of t minus 1 of x. So this is yi minus f of t minus 1 of x minus alpha t ht of x squared. Right? And if you set it, this quantity, yi minus f of t minus 1, this is the error that was being made at iteration t minus 1. Right? This is what the ground truth was. This is what at iteration t minus 1 they were predicting. Up to the weak learners up to this. So let's just call that e of t minus 1, ei, error of the ith point at time t minus 1. Right? So this is 1 over n summation of I equals 1 to n ei minus alpha t ht. Very nice. There'll be just one more observation, and then that will start looking exactly like this. So the observation that I'll claim is this is a regression problem. So the output is a continuous value from minus infinity to plus infinity. H already has a scale, right? That's the number from minus infinity to plus infinity. So it doesn't need another scalar multiplier. Right? This scalar multiplier can be inside this thing. It's just W transpose X, so alpha times W transpose X isn't going to change anything. So I can sort of have a canonical alpha, so I can just say alpha T is equal to 1. Right? It's just canonical scale. Combine these things at canonical scale. Does that make sense?
Why doesn't the HT of X have Xi, X of I?
Sorry, that's thank you.
Is it another minus? This should be really the above.
Before the parentheses.
Before the parentheses.
Before the what?
There's no minimization.
There is a line.
Oh, the minimization?
So between the summation and the parenthesis, the one above.
Stand up and show it.
That's just okay. Sorry. Alright, so if I just hold the scalar constant to 1, and if I just sort of erase that from here, that's pretty much it. Like, this is all I had to do. At this point, this is this problem, except what it's asking you to do is don't regress to the ground truth, regress to the errors being made at the previous iteration. Right? So if we were doing well, that means up to t minus 1 on this ith data point, if we were doing really well, so error at t minus 1 was 0, then just don't do anything at this data point. I want you to predict 0 at this data point so that when I combine you with everything else, you don't mess up what we've already solved. But if we were making large errors at this data point, then when I add you to the ensemble, predict something such that when I add you in, you're going to predict the correct thing. Right? So focus on the mistakes being made so far, everything that we've gotten right, don't try to change it. Right? So this just means call your black box, call least squares with yi equals ei. And regress to the errors being made up to this point. Does that make sense? Yes.
If the errors are high, how will the error be reduced because it's trying to regress to that error?
Because if the error is high, and let's say you do a perfect job, you're not going to, but because it's a weak learner. If the errors are high, so let's say it is able to regress to EI, right? H sub t, the weak learner t, is able to regress to EI. What happens when you add this in? Right? Then this summation becomes equal to yi. Right? So you're regressing to exactly what was missing from the previous iteration. Does that make sense? So it's still the same training data set. Every data point is equally important, but the ground truth for each data point has been replaced by the errors of the committee up till the iteration t minus 1. Does that make sense? Okay. So this is known as L2 boosting. Right? If you can do one round of least squares or whatever, train a decision stump, then you can do multiple rounds. All you have to do is train one, compute its error on every data point, make that error the ground truth, train another one. Right? And just average all of those. We already set alpha t equals 1. Just average all of those, you get your strong learner. That make sense? Okay. This was regression with squared loss. You can also think of classification with exponential loss. So now H is a classifier. It gives you, yi equals +1 or -1. You measure, or it gives you a score for how likely that is, and you have a loss function that measures how well you're doing, and you have a black box that can do that minimization. And this time you can derive a similar algorithm, and that's homework 4. And that's really difficult to do that in 10 minutes, but that's why it makes for an excellent homework assignment. So it's doable. You can derive something very simple. You train sort of one weak learner, which will be decision stump again, and you'll make multiple calls to that. And it has this really nice guarantee that if you can do infinite rounds of boosting, assuming no label noise, right? Nowhere in your training data does it happen that the same feature is labeled with 2 different labels. Then you can actually achieve 0 training if you keep doing boosting. And therefore you need to do early stuff. Okay. So at this point we're done with ensemble methods. We've looked at 2 different kinds, bagging and boosting. You should know when to use which one. You should know under what assumptions they work, you should know the general philosophy that in one, we are trying to take weak learners and we're trying to make them stronger and on a spectrum, right, all the way to an overfitted learner. And in the other, you're starting with an overfitted learner and you're trying to reduce the amount of overfitting by averaging a bunch of overfitted learners. Okay. So now let's move to a different topic. Yes?
The weights haven't, how we pick the weights into this?
The weights, the alphas, if you mean?
W, that we added.
So in L2 boosting, W's don't play a role. Every W is 1.
Okay.
In ADA boosting, which is classification with exponential loss, there is an octet rule that you will derive in O. You'll say, here's, you'll look at, and I'll tell you the intuition. The intuition will be exactly the demo that we saw. Here are the data points that are correctly classified, here are the data points that are incorrectly classified. The incorrectly classified, their weight needs to go up, and the correctly classified, their weight needs to go down. So at the next iteration, you train a weak learner that tries to get the previously incorrectly classified correctly classified.
Okay.
Does that make sense? Okay. So at this point, looking back, we have done supervised learning to as much as we could. Right? We've shown you a whole bunch of techniques for regression and classification. We've even gone like meta machine learning. Right? How do you combine different supervised learning algorithms? At this point, it's sort of good to take a step back and ask, what does this all mean? And if I am a practitioner, can you give me some sort of guarantee that when I do well on my training data, that there will be some guarantee that this is going to work on test data that I don't have access to right? So that's that falls under a branch of machine learning called learning theory. And more specifically, there's a topic called probably approximately correct learning or pack learning. Right? It's double hedging against with two different keywords. Formally, it means what sort of guarantees can we give, and this often comes up when people really want to deploy algorithms and they need domain-specific guarantees. I'm going to ship this out. You need to tell me that the failure probability of your system is less than something. Right? You need to give me a certificate now, right? And that's what we're going to talk about. And this is this idea of how good is our classifier and when is my classifier good enough, right? And we're going to talk about this in a very specific case, in a simple case, because just the simple case is going to be difficult enough to analyze. So the simple case is going to be classification, and we're going to talk about a finite hypothesis class. So this was a hypothesis class that was not finite. It contained in it a threshold, and therefore that's what made it infinitely large. What are finite hypothesis classes? For example, decision trees. Right? This is a decision stump that with continuous features. But if you have discrete features, then you have a finite hypothesis class. Right? Because each feature takes some k number of values, you can split on some feature in some order, it's a finite hypothesis. It may be exponentially large in the number of features, but it's finite. Right? Let's restrict our discussion to that. With a finite decision class, with a hypothesis class, you can ask a question. Let's say I get 0 training error, right? And let me call that, my hypothesis H is consistent with training data. Right? That's what I'm defining. Can you give me, let's answer this question. What is the probability that H has more than epsilon true error? So what I mean by this is I got a training data set, I get 100% accuracy on this training data set. Now when I deploy this out in the wild and I get a new data set that is sampled from that distribution, that true error, what is the probability that that true error will be greater than some epsilon, some number that we are concerned about? Does that make sense? We get the setting so far? Okay. And here's a well-known result that we, here's a well-known result that we won't actually prove. It is easy to prove, but I don't quite want to go through all the details of it because it doesn't explain. Going through the proof doesn't actually illustrate much in that case. But here's something that is well known, and it's an old result, that if you have a hypothesis class which is finite, you train your data set D with n samples, for any learned hypothesis that is consistent, which means it gets 0 training error, the probability that the true error is greater than epsilon is upper bounded by some quantity. This sort of a statement is the goal of learning theory. This is called a generalization bound. It says if you do well on training data, we can give you a probabilistic guarantee that you're going to do well on test data. It can never be an absolute guarantee because training data is itself a sample from the distribution, right? So and the new data set that you're going to see is also a stochastic quantity. So we can only give you probabilistic guarantees, and the guarantee is an approximate performance guarantee, right? With respect to some error. That's why it's probably approximately correct learning. Does that make sense? So the probability that your classifier, which is performing 100% of training data, will make mistakes more than epsilon is upper bounded by something which is the size of your hypothesis class and an exponentially decaying quantity e to the negative of n times epsilon. Does that make sense? So we haven't told you how we came to this. It's not that difficult to derive, but let's make sure we understand this statement, right? First of all, it smells right? It sort of behaves correctly. It has the right trends. Let's think about what this means. N is the amount of training data that you saw. This is saying that if you actually saw infinitely many data points at training time, then e to the negative infinity is going to 0. That's the upper bound on probability. The probability that you will make error greater than epsilon is going to 0. That's nice. Training time, I didn't make any errors. Infinitely many data, I'm not going to make any error at test time. Right? So far so good. Behaving correctly. It's also saying that this bound is going to depend on the size of the hypothesis class. If you have an extremely simple learner, the size of this hypothesis class will be small, and so the bound is going to be tight. This is explicitly telling you what we've been calling estimation error. If you have an extremely deep decision tree that you have to learn, you're going to need a lot stronger N to get this product to be the same than if you have a shallow decision tree. Does that make sense?
So if N is very small, then the probability that it will make P or greater than epsilon is small?
Yes. Yeah, that's what this is saying, right? I mean, this is an upper bound on the probability. If H is a small thing, then the probability that you get... Anyway. The probability that you're greater than epsilon is going to be a smaller number as well.
So that means it's a good thing to have a small hypothesis.
It is a good thing to have a smaller hypothesis class. The caveat is a smaller hypothesis class may not necessarily lead you to zero training error. Right? And soon we're going to generalize this relation to not just have zero training error, but you have some training error t, what is the bound on the test error, and that generalization bound will explicitly tell us the trade-off between going to a higher one. Does that make sense?
Are we going to optimize this as well?
Are we going to optimize this? So it's interesting that you ask that. SVMs, which we started from a completely geometric argument, can be viewed as minimizing the upper bound of the generalization error. You can actually show SVMs, we won't get to that, because one of the things is SVMs have an infinitely large hypothesis class, right? Because it's a continuous weight vector is W, there are infinitely many things. Turns out that you actually don't care about the number of parameters, even though there may be infinitely many. You care about how complex is this hypothesis class, and that's something called VC dimension. And we definitely won't get to it today, but there's going to be a term here that's going to be proportional to VC dimension, and that's going to contain a norm somewhere. And therefore, minimizing the norm is going to minimize the upper bound on the generalization. Does that make sense?
So what's epsilon here? The number of...
So epsilon is like error. So think of this as you get a new data set, it has 100 points. What is the percentage of those points that you get correctly right? Yeah. So think of it as a number between 0 and 1. So epsilon is between 0 and 1. So what is my accuracy on new?
So that's pretty important, right?
That is extremely important. So if I set, and this is where, so I want to give an accurate picture. Most machine learning papers that you pick up, like if you read ICML or NIPS paper, most machine learning papers will not contain a generalization bound, even if they can propose a new method. There's a whole different subcommunity, there's called Conference on Learning Theory, where they'll come up with new bounds for existing models or old models. And it's often, here's a way to destroy a bound. Just plug in all the numbers on this side, and you often come out with a bound on probability that's greater than 1. Right? So like the size of the hypothesis class, e to something, n, if maybe there are constants here, you plug this in, and the number that pops out is something that's greater than 1, which is a vacuous bound, right? Yeah, I knew the probability was less than 10. Thanks, genius. It's not telling me much. But usually the point of those things is the order of dependence on those quantities. Epsilon is exponentially decaying, n is exponentially decaying. Hypothesis class is a multiplier to that. Right? Does that make sense? So here's how usually you end up. Right. So this is basically just saying that even if h makes zero training error, it may make errors. Here's how you usually end up using these bounds. There are two general cases. You might say that, I know that's the upper bound. I'm willing to live with some probability of error on test data. How many training samples do I need? Right. So this is. Let's see if I can do this. Here's one way that this bound is commonly used. This is the upper bound on the probability that you're going to make a mistake more than epsilon. The mistakes are going to be of size more than epsilon. You say here's the probability that I'm willing to work with. There's a 5% chance that I'm willing to, right? So that I'm willing to have an error greater than 10%. Right? And so what you would say is, if this is how much training data do I need in order to guarantee this? And so what you do is, okay, log of h minus n times epsilon is then upper bounded by log of delta, and you would say that n is greater than equal to log hypothesis class minus, so just delta here, divided by epsilon. So you come up with a lower bound for n. You say if you want 10% test error with some 5%, the probability of failure being 5%, then here's the smallest amount of training data points that you need to see when you need to get 100% training accuracy. Right? So this is one way of using it. And so this kind of answers your question. Epsilon is really important because the amount of data you need is order 1 over epsilon. Right? So if you want a tighter bound on the test performance, you need order 1 over n samples. But you only need order log 1 over n, 1 over delta, or the n is dependent only on log 1 over delta, not 1 over delta. Does that make sense? There's another way of using it. If I know I only have 1,000 data points, what's the error bound that you can give me with some probability? Right? That's the second way. Does that make sense? Okay. Okay. I can tell you the epsilon, right? Is that what you would say? So that's the error that you're making. So that's the question that he asked as well. If I measure on some test data point, let's assume this is binary classification. So what percentage of the test data are you classifying correctly? So if you don't think of it as a percentage, think of ratio. It's a number between 0. Okay. And so think about. So the good thing about this bound is that I actually didn't tell you how we derived it, but it holds for all finite hypothesis classes. Doesn't really matter if you're talking about decision trees of depth 1, depth 2, or whatever, right? It actually holds for all data distributions. There's nothing that in proving this bound, and you can go back and look at the proof of this. There's nothing that you assume about the concept that you were trying to learn. Is it an easy classification problem? Is it a difficult classification problem? Am I trying to learn random noise? doesn't matter. If you end up learning random noise with zero training error, we can give you a bound in the testing. Right? So in some sense, it also means that the bound is perhaps not as tight about realistic bounds, but this is a problem agnostic bound. The weakness of this is, of course, that it requires a consistent classifier, something that gets zero training error, and it only works for finite hypothesis spaces. Because if you plug in infinity there, you don't have a bound there, right? So the first one we can easily relax, and we won't tell you how this is done, but this is really possible. You can convert this now into a probability of true error minus train error greater than epsilon. So my classifier works this well on this training data. How well is it going to work on test data? If the difference is greater than epsilon, that's upper bounded. There's an extra factor here because now the proof technique has changed. We're using something called a Chernoff bound, but you actually end up getting this sort of it's qualitatively very similar. And if you just swap terms around, you end up with a bound that looks like this. That if you're willing to accept probability of 1 minus delta, you get that the true error is upper bounded by error of train plus log hypothesis plus log 1 minus delta 1 over n. This is very similar to what we derived, just that there's a square root now because of that 2, and there's the train because we were talking about true minus train. Right? This is a generalization bound. This is the type of guarantee that learning theory seeks. This says, here's how well you were doing on training data. This is the kind of classifier that you were using. This is the quality that you're willing to accept. Here's what we can say about how well you're going to do at testing. Right? And when you stare at that, this explicitly tells you the trade-off between a weak learner and a strong learner. If you use a weak learner, this will be small, but this will be large. You're going to make more training error with a weak learner. If you use a strong learner, you're going to probably get zero training error, but your hypothesis class will be large, and therefore this bound will again be large. Right? And this is why we've been looking at those curves of strong to weak learner, training error going down, validation error going down and then up. Because we've been using it as a proxy for this. That training error is not the only thing that matters, there's also this generalization bound. And that bound tells you that higher hypothesis spaces are not the best thing to use. Does that make sense? Okay. Yeah, and again, this pack bound holds for all H. And interestingly, this holds, but it doesn't actually guarantee that whatever algorithm that you're using will actually find a hypothesis. Right? That's optimization error. So everything that we were talking about here is statistical estimation error. You have an algorithm that finds your training error. We can give you a bound on how well you're going to do a test error, but there's no saying that you will be able to find a learner that actually does this one. That's in the realm of optimization. Does that make sense? Okay, so let's stop here. We'll pick up from here next time. Actually, at this point, we're essentially done with supervised learning, and on Monday we'll talk about your projects, and then we'll pick up on